In this video, we will learn how to determine the empirical formula of a hydrate. And before we get started with the math, it's important that we understand what a hydrate is. So if I look at this hydrate, and this is going to be copper sulfate, copper 2 sulfate specifically, and you may notice that there's this dot, and that dot does not mean multiplication or any sort of math. What that dot means is that there are 5 water molecules that are sort of in the crystal structure of your copper sulfate, but they're not actually bonded. It's a very weak attraction and not enough of an attraction that we call it a bond, and so we put a little dot to separate. And then the prefix for 5 is penta, so we call this copper 2 sulfate penta. And then water, we're just going to call hydrate. Okay, and what we can do is that this interaction between these waters and copper sulfate are so weak that if we heat, and remember that's what the triangle above the yield sign means, if we heat it just a little bit, so maybe under a Bunsen burner, water has a boiling point of 100 degrees Celsius, so we can actually get those water molecules to evaporate away. And what will be left is just copper sulfate, and that's an ionic solid. Ionic compounds have very, very high boiling points, and so we're not even going to get the copper sulfate to melt, even if it's 700 degrees. So if we wanted to get the molar mass of this hydrate compound, what we would do is get the molar mass of just CuSO4. And so if you go onto the periodic table, that'll be approximately 159.61 grams per mole. And then we would get 5 times water's molar mass, and you may remember water's molar mass is 18.02 grams per mole. And then we just can add that to the 159.61, and this would be the molar mass of CuSO4 little dot 5H2O. Okay, so that's how you get the molar mass of a hydrate. A lot of chemistry students, when they first see that, that's a little bit strange, but I'm sure you'll get used to it in no time. Okay, so what we want to do is a couple example problems on how to figure out exactly what this number is going to be. So with this copper sulfate here, it happens to be 5, and that's what the math will tell us. But in this first example we have here, we've got nickel 2 sulfate, and we don't know how many waters. So I'm going to go through how I do a problem like this, and that it pretty much applies to all of these hydrate problems. Okay, so what I've done is I have nickel 2 sulfate, so that's NiSO4, and then some dot, and I'm just going to put a number sign for some amount of water. I don't know if it's monohydrate, meaning 1 water, dihydrate, meaning 2 waters, trihydrate, tetrahydrate. I mean, it could be a lot of different things. And what's going to happen is just heating it, and I'm going to end up with NiSO4 solid left over. That's called the anhydrate. And then I'm going to have evaporated some amount of water, and I don't know what that number is until I do the math. Okay, so if I go through and I read this problem, I'm given 1.082 grams of nickel 2 sulfate hydrate, and that's before it was heated. So what that means is this guy right here, this is 1.082 grams. And then I heat it, and after heating it, the anhydrous material, or the anhydrate, is 0.596 grams. And I'll write that here, 0.596 grams. And I need to determine the formula of the hydrate. So I'm going to circle that because I like to circle what exactly we're going to find. Okay, so we are going to need to get this number, the amount of water grams that was lost. And it may not seem clear right now, But according to the law of conservation of mass, we're not going to gain or lose any mass in a process. And so if this before was 1.082 grams, this after also needs to be 1.082 grams. So what I know is that the water will be 1.082 grams minus the 0.596 grams of the anhydrate. And when I do that math, I get 0.486 grams. Okay, and so I'm going to highlight the numbers that are really important moving forward. Okay, so what I'm going to do here is I'm going to do percent to mass. We're given the mass, so that step has actually already been taken care of. And then I'm going to do mass to moles, divide by the smallest one. And with hydrates, you never have to multiply till whole. And so I don't have to worry about that fourth step. So the only difference with hydrates is I'm not going to worry about each individual element like I do in a normal empirical formula question. What I'm going to do is I'm going to worry about the anhydrate and then the water. So let's see how this looks. Okay, let me move down here. And I'm going to take 0.596 grams of NiSO4, and I'm going to convert that to moles. And according to my periodic table, there's 154.75 grams of NiSO4 in every 1 mole of NiSO4. And that equals a number, and I'll plug that into my calculator here in just a minute. And then 0.486 grams of water, and I know the molar mass of water, that's one that we see commonly. Water is 18.02 grams in every 1 mole of water, and the math tells me that I get 0.00385 moles of NiSO4, and then I get 0.0269 moles of water. And then now I'm going to look at my numbers, and I'm going to divide by the smallest one, which happens to be the NiSO4. So divide by 0.00385, and then divide by 0.00385. And when I do the math, I get 1, of course, for NiSO4. And then I get 6.99, which is approximately 7 of nickel 2 sulfate. And so that's my answer. NiSO4, 7 water. So this is a heptahydrate. And then the last part is that I need to determine the molar mass, but that's not going to be hard whatsoever. I have the molar masses. I just have to add them together. 154.75 for nickel sulfate, plus water. Water is 18.02, but I have 7 waters, and so let me plug that into my calculator. And I get 280.89 grams per mole, and that question is done. Okay, so let's move on to one more. And in number 2, what I have is I have a hydrated crystal, and it gives me percents here, and I've got 89.2% barium bromide, and I've got 10.8% water. So what that means is I've got some barium bromide, BaBr2, and it's got some amount of waters. I don't know how many that is. And what I'm going to do is I'm going to heat it, most likely in a crucible or an evaporating dish, and I'm going to get some barium bromide solid. That's an ionic compound. There's no way we'll get that to evaporate away or even melt. And some amount of waters. We don't know how many waters, and those will evaporate away. And what the problem tells me is that this right here, this is 89.2%. I don't know what the mass is, but I know it's 89.2% of the mass. And this water is 10.8%. Okay, so we're going to go through our steps: percent to mass, mass to moles, divide by the smallest one, and we should end up at our answer. And so we're going to take 89.2% barium bromide, and I'm going to convert that to 89.2 grams of BaBr2. And when I get the molar mass of BaBr2 is kind of a lot. It's 297.13 grams of BaBr2 in every 1 mole of BaBr2. And then I'm going to take 10.8% of water, and I'm going to convert that to 10.8 grams of water. There are 18.02 grams of water for every 1 mole of water. And when I plug this into my calculator, I get 0.300 moles of BaBr2. And when I do this for water, I get 0.599 moles of H2O. And remember, we're not at we haven't done divide by small just yet, so I don't need to round this one. I know it's so close that it's probably not going to make a difference if you did, but I don't technically need to round just yet. When I look at my moles, my anhydrate is always expected to be the smallest moles, and it is here. And so what I'm going to do is divide each of them by 0.300. And when I do that, I get 1 for barium bromide, and I get 2 for water. So my formula is BaBr2, and this is a dihydrate. And then to get the molar mass, again, don't do more work than you have to do. We're going to take 297.13 grams per mole. That's for barium bromide. And then I'm going to add to it 2 times 18.02 grams per mole. And when I do that, 297.13 plus 2 times 18.02, and I get 333.17 grams per mole.